Hello everyone, welcome to ISEKPC 2020 conference presentation. I am Suman Biswas. I am a computer science PhD student in Iowa State University. My supervisor is Professor Ridesh Rajan. Today I am going to present our paper on fairness of machine learning models. We have conducted an empirical study on the fairness exhibited by real-world models, their mitigations and impacts. So what is software fairness? A software is unfair when it discriminates people based on their societal attributes such as race, sex, or age. We call these attributes protected. And when some privileged individuals or a group gets systematic advantage from the decision of the software, it is not fair. For example, when a bank approves a loan based on the records of the client, it should not discriminate based on the race of the individuals. At present, a lot of data-driven software are being developed. Many of these software affect human lives directly. For example, now we use data-driven software in career approval, hiring employees, making admission decision of applicants, and even in jurisdiction of courts. In our transdisciplinary Tripods Institute D4 at Iowa State University, we asked this broad question: how to make data-driven software more dependable? Recently, many of such data-driven software have been reported to show unfairness. Next, I am going to talk about such few incidents. In the first example on the left, Google Translator has found to show bias while translating from English to Turkish and then again Turkish to English. So, Turkish language has no separate gender pronouns for men and women. When translating these two sentences from English to Turkish and then again from English to Turkish, the translator assigned she to a nurse and he to a doctor. However, the original sentences had the opposite pronouns. In the second example, in 2015, Amazon used a secret AI tool to filter their job applicants. And that tools was reported to discriminate between men and women, especially recruiting engine was penalizing the resumes of women to some extent. These things can happen knowingly or unknowingly, but we have to develop methods to avoid such unfair things. This is another example. So Compass is a software developed by a company called Northpoint. The goal was to predict future crime risk of the defendants. It has been used in many US states such as New York, Wisconsin, California, Florida, etc. A study showed that the software is discriminating between white and black people. Here are three different such cases. The software assigned low risk to the person on the left and high risk to the next person. However, the person on the left had the history of two armed robberies and one grand theft. On the other hand, the person on the right had history of only juvenile misdemeanor, not any serious record. But the machine learning models predicted high risk for the African American person. A similar thing happened for the other two cases. If we look at the overall prediction in this table bottom, we can see that discrepancies in the prediction between white and African American. 44% of the African Americans have been labeled higher risk, but they did not reoffend. For the white people, this percentage is almost half. So it is evident that we actually need software engineering methodologies so that we can avoid this kind of unfairness in machine learning based software. In recent few years, a number of studies have been conducted in this area. Mainly three different communities looked at this problem in detail. The first is the machine learning community, who proposed the theory and proposed metrics to measure unfairness. Also, a few bias mitigation algorithms have been developed from the ML researchers. And second, based on surveys and interviews, research on ethical aspects have been conducted by human-computer interaction community. They try to understand how fairness is perceived. And third, the software engineering community has mainly focused on fairness testing, especially automating the test case generation to detect bias. However, we are not aware how much unfairness exists in ML models from practice. What are different software constructs that are related to fairness? So we conducted an empirical study on software engineering aspects of fairness. Here is an overview of our work. We wanted to study how fair the models are wrote by the machine learning practitioners. So first we created a benchmark of appropriate ML models from wild, and then we answered these three research questions. The first question is, do the models exhibit bias at all? If yes, how much, according to different definitions of fairness? And the second argue is, what are the root causes of unfairness and what mitigation techniques are successful? And third, while applying the mitigation techniques, what are the side effects and impacts we observe? Now we'll talk about the methodology of our empirical study. Before going into the details of our evaluations, here we give an overview of the benchmark. So for creating the benchmark, we have collected models from Kaggle. Kaggle is one of the most popular data science platforms where one can host a competition and take part in that. Until now, there have been posted a few hundred of competitions in Kaggle. Each competition offers a prize money and users can participate to solve those problems. Also, apart from the competitions, users and organizations also upload the dataset and task on Kaggle. There are more than 30,000 datasets on Kaggle right now. We have gone through the Kaggle task and identified five dataset tasks that are appropriate for fairness study. To do that, we have identified datasets used in previous studies, and also we have found a couple of new tasks. We have gone through the process of filtering and then manual slicing to create the benchmark of top rated models. Finally, we got 5 different tasks and 8 models in each task, so 40 models in total. Many fairness definitions have been proposed in the literature. There are two main definition categories: group fairness and individual fairness. Group fairness is, as the name suggests, measure the fairness among different protected groups. For example, if sex is the protected attribute, men and women are two different groups, we should evaluate that whether the prediction is similar for men and women. Individual fairness, on the other hand, does not consider groups. It is also called the counterfactual fairness. Two valid inputs should receive similar outcome even though the input differs in protected attribute. That is individual fairness. So next we are going to discuss about those metrics. For each of those metrics, we need to first select the privileged group and favorable outcome of each classification task. Privileged group is the group that has historically been at systematic advantage. So a recent paper described 21 different metrics to measure fairness. We also tried to use a representative list of metrics and compare the fairness. Actually, different metrics are needed to understand different aspects of fairness. Different metrics are suitable for different circumstances or context, or for different stakeholders. From previous studies, we have selected these 7 metrics. The definitions are based on the probability of rate of classification. Here, y is the prediction level, y equals 1 if the level is favorable, otherwise y equals 0. Z is the protected attribute, z equals 1 if it is privileged, otherwise 0. Therefore, here in disparate impact, it measures the ratio of probabilities that privileged group gets favorable outcome to unprivileged group gets favorable outcome. SPD is a similar metric, but instead of measuring the ratio of two probabilities, it takes the difference of these two probabilities. The other metrics also tries to capture different disparities between groups or individuals. After the detection comes the mitigation. In the machine learning literature, 3 different kinds of algorithms have been proposed to mitigate unfairness: pre-processing, in-processing, and post-processing. As the name suggests, pre-processing techniques are basically applied before the model is trained, mostly on the training dataset. Post-processing, on the other hand, take prediction and modify the prediction to some extent to make results fair. The in-processing algorithm operate on fairness our model during the training is done. In our empirical evaluation, we have used 7 dominant mitigation techniques on 40 models. So right now I am not going into the detail of these algorithms. You can just go through the paper for more information about those. All right. So until this point, we have selected the metrics, mitigation algorithms. Using those models at hand, we have conducted this experiment setup for the models in our benchmark. Basically, for each model, first we have evaluated the performance as well as the fairness of it. Then we try to improve the fairness using the mitigation techniques. Now we will go over the findings from our first research question. What is the fairness measures of the model? In this figure, we have plotted the fairness according to different metrics. These are the metrics we use to measure fairness. If the metric is less than or greater than 0, bias exists. The positive bias denotes that prediction is biased toward unprivileged group, and the negative bias denotes that the prediction is biased towards privileged group. If the value of a fairness metric is close to 0, then there is no bias. We have noticed that the models in the same dataset category shows similar bias pattern that confirms in most cases the bias is ingrained in the data itself. But there are a few models that can also avoid the bias. For example, in this one, BM5, it is a more fairer than the other models in this category. Here we have plotted the performance in terms of accuracy and F1 score, as well as the total bias of the models. It shows that fairness has a cost in most cases. It means that some models are fairer, but they are losing accuracy. However, there are some models too that are retaining the performance along with having fairness. As an example, this model SE6 is more accurate than most other adult census model. At the same time, it is also fairer than the most others. We have pointed out that this is an optimization problem and more research is needed to better understand the trade-off. We also found instances where developers try to optimize model towards performance, which directly affect fairness. Here, GC1 and GC6 both are actually random forest model. They are optimized through similar grid search with different hyperparameters, but they are so different in their fairness. In fact, GC1 is much fairer than GC6. We identified that the reason to this is GC1 is optimized for recall, whereas GC6 is optimized towards precision. As a result, GC1 has more false positives and the false negative is less. Therefore, it mitigates the bias. The implications that we observe are developers should optimize carefully, and the optimization should be available to different groups as well. Here is another example which shows that fairness specification is necessary to give control over fairness to the developers. Take these two models, AC1 and AC2, and they both use the gradient boost, but the fairness values are so different. The reason here is the data is not balanced with respect to male and female. AC1 balanced this data by class weight equals balanced. But the Light GBM library does not provide any documentation on this fairness impact of the construct. Therefore, fairness specification for this kind of model constructs are necessary. In this dataset category, bank marketing BM6 has stand out. It shows much less bias than others. When we looked at the model, we found that before training a support vector classifier, the data has been standardized by using standard scalar method. We have done some detailed investigation, and it turns out that feature like age in this case has such a distribution that dominate over other features. Now, when it has been standardized, the model is less dominated by that feature and becomes fair. Therefore, we should check whether a feature is dominating over other features or not. This is also an interesting one. Sometime a developer can drop a feature if the feature does not improve accuracy. Here, SE6 has used both of these two features, education and education years, that is numerical. But SE5 has dropped this numerical feature and it showed bias compared to the other one. We have also shown that often different metrics provide different fairness signal which could be misleading. For example, look at this BM5. If a person only considers DI, then this model BM5 seems much fairer than others. However, suppose another person considers ERD. That person will take BM5 more biased than others. And the correlation chart also shows that for two different data sets, the correlation of metrics are not consistent. So it is important to carefully select the metrics, and often different metrics helps to see the different aspects of fairness. In some tasks, there are multiple protected attributes. In this dataset, sex and age both can be considered as protected. If one model is fair with respect to sex, it does not necessarily mean that it would be fair with respect to age. Now we will discuss the findings from our RQ2, which is related to the bias mitigation techniques. As we mentioned, we have applied 7 different mitigation algorithms on each of the 40 models. For each of the models, we have picked the best mitigation technique and plotted the unfairness. You can see for most of the models, at least one of the mitigation technique has been successful. We also found a few patterns of the mitigation that we will be talking about. These are the evaluations to compare different mitigation algorithms. We have ranked the mitigation algorithms for each of the model. For a given model, the algorithms before slash mitigate bias and algorithms after slash actually diminishing the fairness. We have also found that models in same dataset often follow same mitigation pattern. Like for the models in German credit dataset, most of the time the adversarial debiasing has been successful. On the other datasets, we also see similar pattern. This indicates that specific mitigation algorithms works on certain types of dataset. Finally, we will discuss the findings from RQ3, which is about the impacts of applying the mitigation algorithms. And these two are the preprocessing algorithms we applied. We found that preprocessing techniques are preferable than others since it does not lose performance of the models after applying it. In the blue rows, preprocessing algorithms, specifically reweighing, has been successful in many cases. And in these cases, the models do not actually lose performance. On the contrary, post-processing algorithms are successful in most of the cases, especially the reject option classifier. Um, However, we found that these post-processing techniques cannot retain the accuracy as the pre-processing algorithms. Therefore, we conjectured that pre-processing algorithms are preferable than the others. We have also compared the impact of mitigation algorithms on different categories of models. The lower rank means it is more successful. So this column is for at the least biased models, and this column is for the most biased models, and this one is the overall mean rank of the models. So if we look at the mitigation algorithms, clearly pre-processing algorithms are effective on at least on least biased ones, and post-processing ones are effective for the models that are originally contain more unfairness. To summarize, the most important finding is there is a large gap between the fairness research and practice. We need more library support and specification to control model constructs while programming. Also, until now, it is not clear that what is a good fairness threshold and which metric to use for a given task. So further research is needed in this direction as well. Our evaluations also suggest that by leveraging existing techniques, it is possible to build automated tools to localize fairness issues and repair them. Two basic repair point is the data itself, and second, the model which is trained. Finally, choosing the mitigation algorithm and resolving the trade-off is an optimization problem, and still further research is needed in those directions. Thanks a lot for attending the presentation. You can get the preprint of the paper by typing this link or scanning the QR code. The artifact is also available in the GitHub repo. Thanks again. Bye bye.